Good morning. Yeah, thank you. So, is Heaviside dissing Faraday or not?
He calls him ignorant.
Yes, he does. But Faraday was ignorant of mathematics because he came from a very poor family and was apprenticed early to a bookbinder. So he never had the opportunity to be educated beyond sort of grammar school. He never learned mathematics beyond arithmetic. And yet he was one of the top experimental scientists of all time. Yes, sir?
He's definitely not dissing Faraday. He's saying that he's a genius in a way because he's ignorant. Because he hasn't been taught to think like mathematicians do. He's thought of a better way.
So he is opining that, in fact, what Oliver Heaviside is saying is that he greatly admires Faraday, and that Faraday, because he was not bogged down in the niceties of component mathematics, actually thought about the physical quantities that are vectorial in the proper way, which allowed him to make so much progress in experimental science. So I bring this up not because I'm going to tell you all that you're ignorant. In fact, you're way less ignorant than Faraday was, but that the real punchline at the end is that when we're dealing with vectorial quantities like velocity, force, momentum, acceleration, the truth lies in the full vector, and oftentimes the way to analyze is using the full vector and not tearing it apart into components. But we, being not ignorant of mathematics, will sometimes be the scoundrels and tear things apart into components, because that may make things easier as well. You'll learn a lot more about Faraday, who was amazing, next year when you study electromagnetism, because his seminal contributions were in that field as well as electrochemistry. So where have we come from and where are we going? Today you're going to learn about the great power of the Newtonian formulation. So I'm going to remind you of what we've learned so far, which gets at the three laws of Newtonian mechanics, and we're going to do a bunch of examples. If you haven't been taking careful notes up till now, I think it probably would be a good time to start, because we're going to do a lot of chalky examples today. The first one I want to consider is a rocket is up there in empty space, floating along, and finally decides to shoot some crap out the back in order to go forward. So far, as we have done, what do we know about the change in the state of motion of the rocket if it dumps some stuff out the back?
Center of mass doesn't move.
We have one comment. Center of mass doesn't move. What else? Yeah.
Because there's momentum, initial momentum is zero, because there's more momentum going to the left, so the rocket will propel.
He says that the initial momentum of, I presume you mean both the rocket and the fuel and the combustion products, all that stuff, is zero. It must remain zero. If our system includes the rocket and the fuel, and it's initially at rest, it has no momentum, then the sum of the momenta of all the different parts as we move along in life remains zero unless acted on by something outside of that system. Is there a question or a comment?
Another comment.
Yeah.
So the rocket, all of the mass in our system must remain at m, so mass can't just kind of disappear.
Yeah, we're not going to let mass just disappear. So that's a good point. The initial mass m is the mass of the rocket plus plus the fuel. Okay, so in the initial situation, the rocket's sitting there, then it's going to dump some junk out the back that moves away from the rocket at speed v. I'm going to call the amount of mass that comes out dm. It's going to be an infinitesimal quantity so that we can study, we can develop an equation that describes things that are going to be changing. As he points out, the mass of the rocket can't stay the same if it's dumping mass out the back. So the change, the amount of fuel that's coming, combustion products that are going out the back, in the second picture is dm. The rocket now is going to move forward with a modest speed, dv. And what would be the mass now in the rocket? So this would now have to be m minus dm. And if I apply conservation of momentum, so momentum is conserved, that means the initial momentum 0 must be equal to momentum. I'm going to pick going to the right as positive. And so I'm going to get m minus dm times dv is plus. Now, this velocity is going to the left. I've taken positive to the right, and so I'm going to have a minus u times dm. Do you agree? Once we got this set up, the rest is going to follow. Okay, so I see this negative sign. I'm going to pull this to the other side. We have u dm is equal to m minus dm dv. I now want to ignore this. Why should I be allowed to ignore that? Yeah.
Because it's infinitesimally small.
So is this. See, that's what I'm worried about. So this is going to be infinitesimal. This is infinitesimal, and that's infinitesimal. Can I get rid of this one? Or is that cheating? How many say it's cheating? You're outvoted a lot. Of course, I didn't ask how many don't say it's cheating. Okay? So if this is an infinitesimal quantity and that's one, this product is a lot smaller than this times that infinitesimal quantity. Put another way, if I just compare these two quantities, that's not infinitesimal and this is. And so I can pick my amount of mass to be arbitrarily small and then compared to a finite quantity like the whole mass of the rocket originally, the little bit is negligible. So it's because here I've got effectively an addition operation or subtraction, whereas here I've got a multiply, that I can neglect this compared to that. How many, are you okay with that? Yeah? Okay. So I'm going to have dm. I'll write it out first this way, and then we're going to neglect it, equals 1 over u dv. Okay. Now dm, is this a positive quantity or a negative quantity? Based on how I define things. Yes, please, Professor Chen. She's wondering if I should change this to minus u plus dv. So, and this is u compared to the back of, and again, I can do that, if you like, plus dv. And now, why am I now going to ignore it?
Because it's tiny.
Because,
Why do I get to it? Yeah?
Well, in one way, the DVDM cancels out on both sides. You don't have to ignore it because the DVDM
That's fine. I can either cancel it out, but in the end, it's the same argument that I have here, that compared to a finite large value of velocity u, this change dv is negligible. So I will have dm over m is equal to 1 over u dv. Now, I was asking dm, is that positive or negative? That is positive. That's the amount of combustion products that got thrown out the back. But that causes a change in the mass m that's left in the rocket that will be negative, right? The mass of the rocket that remains is going down. So I will argue that dm, little m, is equal to minus d big M. Do you agree? If m represents the mass that remains in the rocket, if it throws some mass, little dm, out the back, then the mass of the rocket must be reduced by that amount. So I now have minus dm over m is equal to 1 over u dv. Can I solve that? How do I solve that? So I just can integrate both sides. So let me do that. So the integral dm over m is equal to the integral of dv over u. I suppose I should have advanced this. Okay, what about limits? I'd like to put in the limits. What's my starting mass over here? Whatever the m was initially. And so I might come up with some mass at some later time, final. And on the right, I'm going to start at v equals 0 and go to some final velocity for my rocket, okay? So the integral on the left gives me minus the logarithm of m to be evaluated between that initial value and the final value, and that is equal to, u is the constant velocity of the ejected stuff with respect to the rocket. So can I pull that out of the integral? Yes, I can pull that out. What do I get then in this integral? So that will be v final minus initial over u. Okay, so subbing in on the left, I have minus the logarithm of m final minus the logarithm of m, the initial mass, must be equal to v final over u. I think there's a way I should be able to simplify the logarithms here. So minus minus is plus. This is the difference between two logarithms, and therefore that's the logarithm of the ratio. Agreed? So this would be the logarithm of m over m final is equal to v final over u. So I have, I hope, looked up some numbers from my colleague. Whoops. Go back. Yes. So Professor Leisenga is a rocket enthusiast, and he launches rockets. Let me see if I can remember. Okay, so he uses U of about 1 kilometer per second. So you burn this stuff and you throw it out awfully fast. Okay, and a particular rocket of his has an initial mass of 4.55 kilograms, and it loses mass by the time the rocket engine has burnt itself out of 0.65 kilograms. So the question now is, how fast is the rocket going at the end of the burn? Let's see. So I can send that one up, that one up. So V final will be the speed at which the combustion products are ejected times the logarithm of the ratio. The top one is m naught, that's the initial mass. The bottom one is m final, which would be the initial mass minus however much was ejected out the back. So this looks like 1 times 10 to the third meters per second logarithm of 4.55 kilograms over, we have to do a subtraction. What do we get? 3.9? You can see that the units inside wipe each other out. And if we evaluate this, it comes out to about 150 meters per second. Is that fast? What's the speed of sound? About 330. So this is getting close to half the speed of sound for that particular rocket. Yeah, Mach 0.5. And should you get into rocket enthusiasms, you may make your rocket go significantly faster and break the sound barrier. Okay, so let's review. What we did is we conserved momentum, and we had to pay attention to the direction. We kept terms that were first order in differentials. We could ignore, compared to first order terms, second order differentials, and we end up with the rocket equation here, which told us how fast the rocket would go at the end of the burn. Yes, please.
Because we ignored those second order differentials, does that mean the equation's not exact?
So the short answer is no, it does not. That is, if I were to say, let me start up at UDM is equal to m minus dm dv, okay? And I'll even now, for Professor Chen, put this as u minus dv. And I will say this happens in an infinitesimal time dt. So I will now divide by dt and then take the limit as dt goes to 0. All right? So I'm going to take the limit as dt goes to 0. Okay? So this term, u dm over dt becomes what? Keely, what does that come to? So the u is just fine. It sits out there, and I have dm dt limit as dt goes to 0. What do you call this thing? A derivative. That's the derivative of the mass with respect to time. That means the rate at which mass is being ejected. Right? Okay, then I have this term, minus dv dm over dt. Limit as dt goes to 0. So I can pick either one of these things, dv dt or dm dt, to make a nice derivative that is a sensible quantity, right? That's the ratio of two things that are infinitesimal as they go to 0, and that goes to a finite ratio, which is the derivative. But what am I left over with in that limit as dt goes to 0? So then I would have, for instance, dv dt. Perfectly reasonable, perfectly sensible. What do we call that? That's the acceleration times dm, which is going to 0. Right? So compared to this term goes to 0, this term does not when I do my limit as dt goes to 0. So in the limit that we let the infinitesimals go to 0, it's exact. Okay? And we'll see more examples of that later. Yeah?
Up in like middle of the second bullet,
Yeah.
We said that u was constant, but isn't u a constant relative to the spaceship?
Correct.
So won't it change relative to the Earth or the?
Yeah, so at each step of the way, we could, if you like, ask, suppose that we were moving along with a rocket at that moment and watch what happens. Okay, so we're starting moving along. After some time, the rocket's already up to speed v. Fair enough? So now, if we move with speed v, we see the rocket at rest, and we watch another squirt, right? Some more comes out the back, and it moves with respect to us a little bit. So you can always bring it back to the same picture that we have where it's initially at rest. So u is the speed with respect to the back of the rocket, and it remains that way as the rocket's moving along.